So square root is right above the squared button. Bam.
I think the white.
Sorry. Get in there, y equals. Square root, I'm going to get rid of this other stuff. Clear. Square root of x. And everybody also hit zoom 6. Remember, zoom 6 is the one that gives us a standard negative 10 to 10, negative 10 to 10. We hit zoom.
Do you need the parentheses and do the x like that?
You don't have to close it. I just did it to make it look nice up there. Now watch, real quick, watch. You ready? The old dumb calculator software was sort of like Microsoft Word. It tries to guess what the shit you want. It gives you a parenthesis. I'm like, I'll put that if I need it. Shit. But it just gives you one. The newer versions, the square root symbol just grows.
Yes.
That's really nice, right? Okay, so forgive the computer. It's not been updated. So I don't even need to close it. If I hit zoom 6, we'll all have the same picture, hopefully. Let me know if you have any trouble. And this is what we got the other day. Remember, it was a parabola that fell over, lost its bottom half. Okay, how are we doing? Is that decent?
What'd you plug in?
Square root of x.
Mine's something completely different.
Okay,
Oh, you put a square root, you put pi. That's pretty short. So the square root is right above there, so it's second. Yeah, you hit the pi button.
What are we called?
It was doing like a slope of pi. I just hit graph.
Oh, God.
No.
Poor thing.
Boysenberry pie. All right. Is everybody able to get that picture to show up? Everybody's good? All right. So now I want you guys to do this other side. The one we just were working on. The other side is some graphing exercises. I want you to do those. I like it. Number 1, I'm just going to make a real big point of this. Do you see how the plus 5 is not in the square root? See, if you have the old calculator, you've got to close the parenthesis before you put plus 5. Yeah, the new calculator, you have to hit the over arrow to get out of the square root before you put plus 5, or else it's going to be in the square root. You're not going to get the right function. Okay. Everybody see the one we're working off of, right? Everybody's got that? Maybe it'd be easier. Yeah. Do that. Whoa, what the heck? Oh. Oh, yeah. Okay. My staff students were using this last. Oh, yeah, the battery's almost dead for you.
Okay.
We'll give you a battery. Please make sure that the battery's okay on these when you're using them. I don't want it to crap out right in the middle of everything.
Negative x.
Oh, exactly.
What we can have is 0.
Okay, I got your back to where you went.
This way. Positive.
Don't want that one. Do I have my own? Is this me? Yes.
Negative.
Okay, that one's got enough battery to get through today.
Right.
Yeah, and then hit zoom. No, if you hit graph, let's see what happens. Oh, so hit zoom 6. Zoom standard. You see that? It'll always take you back to negative 10 to 10, negative 10 to 10. There, that's the way it should look.
Plot it out, see? No, it would not be negative. You can't. Negative 1 is square root. You can't square root that. But square root of 0 is 0. Square root of 1 is 1. Square root of Square root of 4 and 2 plus 5. Oh,
Use my own calculator so I can this is the way the input should look for the first one.
easy.
See how the plus 5 is not in the square root?
Easy.
Or if you have the older calculator, you got to close the parenthesis before you put plus 5. So then your graph should look like this. Oops. No, it shouldn't. So you hit zoom 6. It'll always take you back to the standard window. So everybody's graph look like this. Now why does that make sense?
Because
How does that look related to the first one we did? It's just the graph has gone where?
up
Up. How much?
5.
5. It makes sense because I took the square root of x. Whatever the outputs were, I added 5 to them. So the whole graph just moved up 5.
You really get what we're doing.
Say again?
You really get what we're doing.
Okay, so the first thing is,
I know what to do, but I don't know what I'm doing.
Like what we're building up.
What is
oh yeah, well that's the purpose of this worksheet, right? Answer the questions in the worksheet, and then we'll summarize, and we'll see if you get what it's trying to say, and if you don't, we'll summarize what it's trying to say. Yes?
It's fun.
Is what
I
now?
don't know. It's just
What will you do?
Describe the transformation.
Don't worry about it. Good. Make sure that it turns on and there's good battery.
Can I grab the second one too?
Now, let's see. Let's do this first one. Let's get this all the way done together.
Okay.
So to graph a rough sketch of this, here's 5, right?
Yep.
Now if you put a 0 in, that's 5. Put a 1 in, that's going to be 1 plus 5 is 6.
Yep. 1 and 6.
And then it just kind of goes from there, right? It's just a rough sketch. Now when I say transformation, do you see how it took the original function and transformed it somehow? It's a really, really simple transformation. Right? Didn't go Super Saiyan or anything. It just took the graph and it moved it, like we just said, up 5. That's all it did. You guys, is that cool? You can see that. You can see that this is 5 higher than it used to be. Right? Okay. So when it says describe the transformation, up 5. Bam. What's the domain of this? You can just see it from the graph. What's the domain?
0.
0 to infinity. I like it. And what's the range? What's the first output that happens? 5 to infinity.
I have a question. So
Yes.
Because it's equal, that's why it's brackets? Or,
Because there's a closed circle there. When you plug a 0 in, when you plug in a 0, it works. So 0 is included.
okay.
And when you get out, you get a 5 out. So 5 is included. There's no open circles there. So you wouldn't put a parenthesis. Yeah.
Okay.
All right, keep going. Try number 2. And the big thing to notice there is the plus 2 is inside the root. We're going to see how that's different.
Okay.
It's not going to take it up 2. It's going to do something different. Hopefully everybody staring at me is done with this.
Oh, it shifts to.
Yeah, exactly.
Addison went down.
Oh, yeah,
Well,
Would you write in the description?
Oh,
Just a 5.
yeah. Yeah, it's a very simple transformation. You can have transformations like it'll reflect it over the y-axis. You can have transformations where it'll stretch it and shrink it and compress it, and yeah, that's for later. These are really simple ones.
But do I want them like that?
So you have the newer calculator. Here's the next one. You want the +2 inside. The older one, if it opens a parenthesis for you, you don't want to close the parenthesis until you get the +2 in there also. So the whole thing is in the square root. So when you graph it, it should look like that. So how is that different from the base square root graph? It moved it
To the left, too.
back 2, yeah, to the left 2. And why does it make sense? Where's the number here? It's in with the x. What direction does x control? The x-axis controls what directions? Left and right. So if it's in with the x, it's going to move left or right. If it's outside, and it could be subtracted. See how the first one I could put that with, I can subtract 5 and put it with the y, the g of x. So that's why it's going to be up and down. Now think about this. Why did this thing move back 2 when it's a frickin' +2 there? This is what students hate, and it's too damn bad, but it only freaking makes sense, though. All of the numbers I plug in can be 2 less than before, because what's the first thing I do to them? Add 2 to them. So that's why the whole thing moves back 2. In fact, what is the domain of this if I just do it by hand? How do I find the domain of square root of x plus 2? X plus 2 has to be, so x has to be greater or equal to -2. It can now, before I had to start at 0. Now it's allowed to start at -2 because the first thing I do to the damn stuff is add 2 to them. That's why you always do the opposite of what it looks like when it's in with the x. It's kind of like reaction to that. Oh, you're adding 2 to me? I can be 2 less than I used to be. So the whole graph moves back 2. Does that make a little bit of sense? This is your first baby steps into this bigger idea of transformations. Yes?
So if it's minus, it's opposite.
Yes, if it was a minus, in fact, do I have the last? Yes, so try the last one. The good guess on this one is that it's going to move forward 4, like to the right 4. Let's see if it does. By the way, real quick, what's the, oh shoot, where did my pen go? There you are. Finishing out this second one, what's the domain of this one? Yeah, the smallest x I can use is -2. We did it algebraically up there. What's the range?
0 to infinity.
0 to infinity. Kicking the ass in. I like it. Oh, describe transformation. Left. All right. And then if you look at number 3, you see how I didn't want to give it away until you did the worksheet a little bit for yourself? So yeah, you're going to go into some shit not knowing what my point is. That's actually my point. I want you to try to discover it yourself. What, Jeff? This one, just going to make this a -4. Make sure you use the minus key, not the negative key, the minus key. Or you're going to get a very different graph. You should get this graph, and it does exactly like we predicted. Everything now has to be 4 bigger than it used to be, because the first thing I do to them is take 4 away from them. So the whole thing moves to the right 4. What's the domain now? Yeah, we see that on the graph, and of course if we did it algebraically, we get x greater equal to 4, which is 4 to infinity. And what's the range? 0 to infinity, inclusive. There you go. I like it. Now what about these last 3? I don't know if anybody made it to these guys yet.
That was good. How do you go from decimal to fraction on a calculator?
Hit the math button. Look at the very first thing.
Yeah, I know, I did that. It didn't work.
Well, it only does it up to a certain size denominator.
So this one right here.
Wait, what happened? How did you get 2.56? Sure. Oh, there it is. Okay, good. Yeah. So that's too many places for it to change into a fraction.
Oh, okay.
It only goes up to a certain size denominator.
But you'd want us to write that as a fraction though, right?
No,
No?
No.
It could be as a
I
decimal?
would say round it to whatever place.
Oh, okay.
In fact, that's rounded because only so many fit on the screen, right? So it keeps going forever.
Oh, okay.
Yeah.
Which one do you use to get like 21 grams?
Oh, wait a minute. Oh, yeah, you're good.
Yeah, it's funny you use something radical on.
What does 728 to the 1/7 mean?
No, I was saying for
No, I know. But what's the 1/7 power mean? What root?
7.
7th root. So if I need to do the 7th root, I can do it as a 1/7 power. So you need to do a 4th root. So you can do it as a what power? There you go. Do that to the 1/4.
Oh, so you can't do it on the calculator.
Yeah, you can. I'll show you. But for right now,
Okay.
I'll show you. But I just want you guys. That's why I did part A. Hoping that would help you with what to do with part B. Yeah. Yeah. So you did 759 though. That's why it's a little bit different. It should be 729, but that's the right idea. Oh shit. So here's 729 to the 1/7. Now, I'm so used to that, I'm still not used to the new calculator. I didn't need to put these parentheses because the new calculator puts things in the exponent, but if you have the old calculator, you do need those parentheses.
Yes.
Because otherwise it'll do it to the first power and then divide that by 7. You got to get this. If you didn't get that number, let me know. Okay. So then that gives me a way to do number 2. How would I do number 2? You don't have a 4th root button that you know of. So how do I do this? Well, that's why I gave you part A. How should I rewrite this? It should be to a what power? 1/4 power. 4th root is a 1/4 power. So if I just type in there point, where'd it go? 1, 5, what happened? 0.0625 to the 1/4 power. There you go, you get 0.35. So if I did 0.35 times 0.35 times 0.35 times 0.35, what would I get? 0.015, blah, 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 right? Because that's what that means. Is it pretty cool so far? Yes.
How do you put the exponent again? How do you on the calculator?
Oh, here's your to the button. That's what I call it. There's your to the button.
Oh, okay.
The little caret is your to the button. Now I'll show you right now. There is a what I call a throot button. A throot. I am throot. Watch it. Here's why I call it a throot button. We want a what root? We want a 4th root, right? So put 4. I'm going to show you 4 math. And do you see the one number 5 that's got like a variable? So you put the 4 in first. That's 4, and then that button is the throot button. 4th root. Hey, all right. That's why you're just so weird. 4th root of point. Oh, I'm not going to do all that shit. It'll give you the same answer. It's the 4th root. Right? So there is a general root button. There is. It's under math. Math sounds like there's going to be a lot of shit in there, and there is. Oh, and what about number 3?
Infinity?
Why? Why infinity? Well, give me 7 then. If there's an infinite number. Give me
Well,
7
because
ways.
the 5 is on the outside. So square root of, I just...
5th root.
Yeah.
So you can either do it with the throot button we just talked about, or you can do it 2x to the what power? 1/5 power. So there's really 2 main ways. So really 2. Well, you can argue you could do 2 to the 1/5 and x to the 1/5. That's basically 2x to the 1/5. It's the same thing. So there's really 2 ways. So you're close. There's more than 1. You guys okay with what's happening? Okay. You lost me. Here's the syllabus. Okay. I just want to bring back the graphing calculator. I can't remember if there's some in the homework about graphing radicals. I think there is. Bless you. All right. Let's get back into some new stuff.
This is 10.3 with graphing.
Let's see. I think graphing is like everywhere in here. 10.1 is where we first graph the radical stuff.
Okay.
So then they can bring it up whenever they want to. 10.2 is the roots as fractional powers, right? 10.3 is one of the most important sections in here. There's a beautiful analogy between fractions and radicals. There's a few of them, actually, to be honest. The first thing I want to talk about, though, is to remind you, when can I multiply two root stuff together? So if I had the square root of 2 times the square root of 3, can I do something with that? What's your gut tell you?
Like square root.
So what do you get?
Square root of 6.
Square root of 6. I love it. If a whole 2 times a whole 3 is a whole 6, a half of a 2 times a half of a 3 is a half of a 6. Well, you guys didn't like that at all. Oh well. So watch. I'm going to overanalyze this thing for a second just to show you why the general rule is the way it is. How do I rewrite 2 square root of 2 with a power?
1 over.
And how do I write 3 square root of 3? It would be 3 to the 1/2. Right? All right, now watch. Can't I undistribute the 1/2 power? Two times 3 to the 1/2, because that's where that would have come from, right? And of course, 2 times 3 is 6, and 6 to the 1/2 is square root of 6. Don't be saying no 3. It's not 1/2 of 6. It's 6 to the 1/2 power. I get upset, my grammar gets even worse. How do you guys feel about that right there? Is that, what's going on?
It makes sense.
All right, so either, of course, hopefully your gut tells you that's what should happen. Square root of 2 times the square root of 3 should be the square root of 6. This is me showing you technically why that's allowed. When could I not distribute that out is if these two were not the same, right? So if they're not the same root, if they don't have the same index, I can't just put them together. So for example, if I have the cube root of 7 times the square root of 3, that doesn't equal shit. You just go, I'm done. There you go. You guys see that? I can't put those together. Why? Why can't I just multiply those together? Because they don't have the same index. One has a cube root, and the other one has a square root. So if I rewrite this, isn't this 7 to the 1/3? And this is 3 to the 1/2. Did they have a single power that was distributed? No. One's got a 1/3, one's got a 1/2. There's nothing I could take out like I could up here. So the roots have to be the same in order for you to be able to multiply them or divide them. How's that?
So you would make it the same.
Huh?
So you would make it the same, right?
I can't just make them the same.
Like by multiplying 1/3 and 1/2 to have similar.
No. All the properties of powers require what to be true about the base? The bases have to be the same. Are the bases the same? No. Is that hard? You guys all right? You can multiply them if they have the same roots. If they don't, you can't. And that's all we've said. And why is that true? Because of this. I'm going to continue because I don't see any questions happening. So what's this? What's the 5th root of x times the 5th root of x squared? Fifth root of x to the 3rd. Yeah, they're both 5th roots, so I can multiply these sides. Now, the one time you can do something if they don't have the same root, it's kind of related to this guy, what I just said. These bases weren't the same, so there's really not a damn thing I can do. But if the bases are the same, like if I had the 5th root of x times the 4th root of x, there is one thing I can do involving writing it in the better form. What's the 5th root of x as a power? X to the 1/5. What's the 4th root of x? And this is what you were trying to tell me earlier, but of course here I couldn't do it because they weren't like bases. But there, what would I do with the powers? Add them. Yeah, so LCD. So it'd be 4 20ths and 5 20ths, 9 20ths. Is that cool?
So it's kind of like adding like terms beginning, because it's like you have the 5. Like, because you have the square root of x times
5th root of x.
5th root of x, and then 5th root
4th root of x. And the fact that the x's are the same tells me maybe I can do something. And since they have the same base, I'm allowed to add the powers.
So either the roots have to be the same, or the bases have to be the same.
For me to be able to do something.
Okay.
I love it.
But
This
it
guy, I
doesn't
couldn't do
keep up.
shit because the bases aren't the same and the roots aren't the same. He ain't got a chance.
Okay, so but you either have to have one or the other.
Beautiful. To be able to do something. I like it. If the roots are the same, that's the best because then you just multiply the insides together. Like, that's awesome. We've already done that. What's 3 times 5?
Which is
Oh, that's the no root of 3 times the no root of 5 is the no root of 15. I mean, they both don't have a root on them, so I'm able to multiply them together. They have to have the same root. Yes?
And how would the question look like? What would they ask you, like, to change it to fractions? Or how would they say that?
They say simplify.
Simplify?
Yep.
So
You have to
simplify
know when you can do something and when to convert to fractional notation. Yes.
So these will also simplify?
Yep.
Okay.
That'll be all they say. Now, sometimes that'd be nice, and I might be also say simplify using fractional exponents. I love when they say that on a test and the person doesn't use any fractional. I'm like, I'm trying to help you. So here, I might say simplify using fractional exponents. And you're like, I don't see any. Well, that means you make them, right? You convert them into that notation. And then you're like, oh, shit, it's just add the powers together now. Sweet. Yes? Okay. What's he missing? A 4. What's he missing? A 5. 4 plus 5 is 9 over 20. I mean, yeah, I'm going to skip that kind of stuff. You guys can do that. Okay. All right. So that's one big thing is I can multiply or divide two roots if they're the same root. And then I can do something with fractional powers if they're the same base. If neither of those are true, I can't do shit. Now watch this. We were just slamming together two roots, right? Like the first thing we did was square root of 2 times the square root of 3 is the square root of 6. Math is notorious for being able to go both ways, right? Don't judge. All right, so here's something really, really interesting. Here's where I'm going to try to make an analogy with fractions. Can you do the square root of 18? What's the square root of 18? I'm not saying you should be able to. Can you do the square root of 18?
Yes.
No. You can simplify it, but can you just tell me what the square root of 18 is?
No.
Shit, no. I don't know. You can guess. It's a little bigger than 16, so the answer should be a little bigger than 4. Square root of 16 is 4, so square root of 18 is 4 point something. It's a little bigger. Is that cool? But I don't want an estimate. I don't want anything out of a calculator. I want you to simplify this. What the hell does that mean, Jeff? Well, if I ask you to simplify this, or to rewrite it, let's say, what would you do? How do you rewrite 11 over 5? What's another way to write it? Yes, 2 and 1/5. Now, how did you do that? Isn't 11 10 plus 1? Now, this is probably not the way you would do it, and I don't care. This is a way to do it, and it actually shows you a lot more of the idea. Right? Is this what I've written so far true? Yes, because 10 plus 1 is 11. And then 10 divided by 5. You do the part you can do. 10 divided by 5 is 2. And you leave the part you can't do. So I leave 1 over 5 because I can't do shit with that. You guys understand that? And I know I'm not trying to go back in time and make this harder than it was. I'm trying to overanalyze what we know is easy so I can apply it to something else.
Couldn't it be 9 plus 2?
No, 9 plus 2 is a little, well, sure, I see what you mean. 9 plus 2, but you wrote it in a way where neither thing is divisible by 5. So here, I want to rewrite 18 in terms of a part that I can do the square root of, and then the other shit that I can't. So if I used, isn't 18 3 times 6? Well, why is this crazy? Because can you do the square root of either one of those? No, that's a bad way. So what's a better way to do 18? 9 times 2. Isn't that true? What's the square root of 9? 3. What's the square root of 2? I don't freaking know. Okay. Right? What's 10 divided by 5? 2. What's 1 divided by 5? I don't know. Let me just write 1 over 5. You see how it's the same idea? Do the part you can, leave the extra shit you can't.
What section is this?
10.3. Yeah. So the idea of simplifying radicals, it kind of feels like reducing stuff in a sense, right? Or this, no? The idea of simplifying radicals is huge. It's big. Bigly. You can do it bigly. Webster's just going to have his head explode. All right. So what about square root of 50?
25 and 2.
Yeah, so you can break it up as 25 and 2, right? Now I can also break it up as 5 times 10, but that's not the smart way to do it because I can't square root either one of those. What's the square root of 25? 5. Square root of 2? I don't know. Now, just to backtrack for a second, let me show you a second way. I'm trying to focus on this way because this way is better, period. Not just because I like it better, because it's better. The other way, people make simple mistakes, but the other way, people like better for some reason. But I'm going to show you it. Here's the other way to do this. What's the square root? Why can't I do the square root of 3? It's kind of a silly question, but I can do the square root of 9. Why? 9 has 2 3's in it, right? The square root's looking for 2 things. Square root of 25 is 5 because 25 has 2 5's in it. You with me? So one way to do this kind of problem is break up 18. 18 is 3 times 6. 6 is 2 times 3. What do you see 2 of? 3's. So I can put a 3 out here, and the 2 stays on the inside. Isn't that the same answer we got over there? People like this because you can just break a number all the way down. You can always do that. But the problem is I get this as an answer. They don't know where to put the 2 and the 3. They just guess. This is bullshit. This makes sense.
And what happens to 6?
No. 6 is 2 times 3.
Okay.
So it's in there. Right? Just break it all the way down to its parts. Whatever it has 2 of can come out. Why do I like this way better? Because you can see exactly what is coming from where. There's no like, well, where do I put these things? There's no question. There is freaking 3 because that's where the 9 is. That's why I prefer this way. So let me give you this handout. It's got both of those ways described on it. You know me. On the other side is some notes on 10.2 if you want it. Focus on the very colorful side here. 10.3.
Thank you, sir.
So I want you guys, we already did the first one together, but I want you guys to work on those problems. Notice that how there's some cube roots down there too. It's the exact same idea. But a cube root requires numbers like 8, 27. Those are cube numbers, right? Okay, we'll see how far you can get with this. And Rita, I gave you both methods to look through. You can pick the one you like better. They both work. I'm just warning you that method